Okay, great. So I'm really happy to introduce the speaker today, Fabian Reich from TU Munich. He's a second-year PhD student in the Department of Energy Management Technologies at TU Munich, supervised by Professor Christoph Goebel. His research focuses on machine learning to model building thermodynamics. These are necessary for training model predictive control for the building, which can reduce carbon emissions by 30%. And I'm very pleased to see model predictive control, which I'm a champion for against reinforcement learning. But anyway, thanks so much for coming and look forward to your talk.
Yeah, thank you so much for the introduction. Today, I won't really talk about model predictive control, but one major path leading that direction, namely the modeling of the dynamics of the building. And yeah, it wasn't easy to find a title for my talk because I wanted to give you a broad overview of what I'm doing and the research group I'm associated with. So it's kind of yeah. So my work mainly focuses on modeling building thermodynamics, and we've done work from data generation to transfer learning. That's why I named it that like that. Okay, so then a little bit about myself. I think most of it has already been said. Just regarding my background, I'm an electrical engineer who focused on power systems control and AI. And I did an energy expert, which is, I'm pretty sure you don't have this in the UK, but this is like an official energy consultant title that you can take when you have a certain degree and you take like a 1-year course. And I did it for residential buildings in order to also use this knowledge for my PhD afterwards. And yeah, and then since 2022, actually, I'm involved in the PhD program at Technical University of Munich in computer science and energy. And yeah, and Munich is down there if you don't know it. Okay, so yeah, I focus in my work on buildings, but yeah, why should we care about buildings? Maybe you know it. If not, yeah, buildings have a very large CO2 emissions worldwide. Around 30% of CO2 emissions come from buildings. And according to studies, these are even going to increase in the future due to electrification in the building. So we have heat pumps, we have electrical vehicles, and thereby the energy demand is going to increase, and thereby maybe also the CO2 emissions. And one way to reduce emissions, but also energy demand, is to equip buildings with intelligent control. When I talk of this topic, intelligent control, I mainly speak of the HVAC system, the heating and cooling system, since this is the largest portion in the building. And yeah, and you can control the building in such a way that you are just more energy efficient. So you would, for example, try to use solar gains, you would use thermal mass, you would try to optimize due to renewable generation or like energy use from the renewables. But to do so, you would need, especially for model predictive control, you would need a model to describe the dynamics of the building, such that you know if you tweak the heating system, for example, what an influence do you actually get on the indoor temperature. And this is a very unique model for the dynamics for each building. So this work, that's what I wanted to show down here. So you have a model F1, and you could use this pretty nicely for a building like that one. But if you would use it for a different one, then it probably won't work that well anymore. So you have a very unique model to each building that kind of makes sense too. You see like every building really looks different. And yeah, so the question is, how do we find F? The most straightforward way would be to do manual modeling. So you would just have an engineer to take some time, model the building in the computer, which just takes a lot of time and it's expensive. So the more straightforward way would be to do this data-driven approach, since it's just cheaper and it's more time efficient. Yeah, the only problem is you would need high quality buildings data to do so. And yeah, and this is mostly what my work is dealing with. And yeah, so one thing I've been working on is data generation, and here's the motivation for it. Because data sets for especially the thermal side of the building are kind of limited. So there are not many data sets that actually have thousands of buildings data in it. And yeah, and if there's a data set, there might be some features missing. And another or some requirements we would have when we want to use data for modeling is like shown here. So one of them would be, for example, to explore the state space. By this, I mean, you would want to have data which explores the state space quite nicely, because when you have real measurement data, the indoor temperature doesn't really change that much, does it? So you have like around 20 degrees and you don't see much of the state space. So that's one problem. Then you would need data for benchmarking for sure. Then you would need data of multiple buildings, and most of the data sets out there only have like 400 or something buildings in the data set, and you might want to show special use cases. And for that reason, so we're probably sure now about this path. You want to have the model of the building. You would probably use data for that, but the question is, where would you get the data from? And now one project we've been working on is to develop Builder, which is a data generation framework for buildings. And that basically works like that you have a configuration file here on the upper left corner. And there you can specify the needs you kind of want to have. How does your building look like? Where's the location? You also can put into the configuration file multiple parameters, like multiple locations, for example. And then you go into Builder and just press play, and then it gets you multiple simulations out there, depending on the configuration file. So you can simulate hundreds to thousands of buildings in like 1 hour, two, depends.
How do you know you're right?
Sorry?
How do you know it's not a fantasy, it's actually real? I mean, how do you know the simulation is a valid simulation?
It was approved according to the ASHRAE test cases.
Okay.
Yeah.
Those are old buildings, because that's quite old data, right? I mean, ASHRAE test cases are from.
Yeah, there are some test cases defined. I'll show you in the next slide. And we approved all of them. And we give a range of parameters. So for the U values, for example, for the heating capacities, which we have approved. And if you go above this range, we can't prove it anymore if it's right, but we are very sure it is. Yeah. So yeah, and then you can use the Model F you received from your building. You can use it for transfer learning, what we're going to do later. You can use it for control, and for benchmarking for sure. So let's dig a little bit deeper into Builder itself. So how does it look like? We have an underlying simulation model based on Modelica in it. So this is kind of how it looks like. And we call it the base model, and you can parameterize it however you want. So you can change the windows, you can change the size, you can change the envelope, that is the U value, the heating capacity, the occupancy. So basically all those parameters, the location, you can change the building parameters, the number of floors, for example, also. And you can change the HVAC parameters. So you can take a cooling system, heating system, ventilation system. And also what's very interesting, I think, is to change the controller also. So you could use it for reinforcement learning also, or for MPC. But you could also generate data, for example, implementing a random controller, or pseudo-random, that explores the state space quite nicely, or stuff like that. Here we just have a small demonstration. So here on the right, you have 5 variations, different locations and different parameters. And here you see the temperature averaged over, I think, the day of maybe multiple days, and then plotted over a year. For sure, when you generate the data, you get it like very high granular, like depending how you want it. But I think at least 5 minutes is possible, but we usually work with 50 minutes data. But yeah, this plot shows you to give you like a kind of a feeling how different the buildings can behave.
So this is a building with no cooling.
Yeah,
just heating alone.
Just heating system.
And it's just, can you do natural ventilation and natural?
Yeah. Window opening and
we can do window opening.
Yeah.
Okay. And do you model like urban heat island effect?
Sorry,
Do you model like an urban heat island effect in the for a city building, you know, the fact that
no, this is not included. But this is actually, we could maybe think about it.
Yeah.
Thank you. Good idea, yeah. Okay, anyways, so we kind of fulfill all of the requirements I showed before. So that we can explore the state space, we can assimilate data of multiple buildings, we can use the data for benchmarking, we can design very special and unique use cases, and you can include all of the desired features you kind of want. And yeah, this is the publication to it. It's going to be published, I think, next week or the week after in the ACM library. And you can already access the link for if you want to use it. And it should be straightforward. Just download it, use the configuration file, and then it should work.
Famous last word. It should.
It should work, yeah. And if it doesn't, please reach out.
Yeah. Thank you.
Okay, then the next project. Oh, by the way, up there you see the kind of the outline of the talk today. And now we moved on to the next project, which we call Gentle or Gentiel. And yeah, so we've seen this slide before. So we try to model the building and get a model for each individual building. Yeah, and one problem is the data availability, since for most buildings out there, we don't have the data. And one option to counteract that is to use transfer learning. And that is illustrated here in this picture. So we assume to have a source building here on the left side, and we assume to have good knowledge about this. That means we have maybe 2 years of data available of that one. We use this data to model it. So we receive F1, and F1 can then be used to control the source building. But also we use F1 for transfer learning. And that means we use it as a starting point for modeling our specific target building on the right side. And therefore we assume to have very little data available. So just like 30 days or something. So that means you would just install the sensors in your target building, wait for a couple of days, use the data, and then you would fine-tune F1 to receive F2 of your target building, and that you could use then for control. And this method already works quite nicely. It's out there in the literature. It counteracts the lack of data, but it leads to inconsistent performance across different sources. So that means when the source and target are kind of very far away from each other, kind of tricky also to say what is kind of far away from each other. But if they are, this method doesn't work good, or it doesn't work at all anymore. And thereby can also lead to negative transfer. So that means you could use other methods in the target to use that little data, and you would actually perform better. To kind of tackle these questions, we tried to develop something new. We called it a general transfer learning model for building thermodynamics, short GENTLE. And what we do here is we use now data of multiple source buildings, not just one, and use data of multiple ones and try to model or try to receive a general transfer learning model named G, which is then used for transfer learning in the next step. And the right step is basically the same. And the research questions we wanted to tackle here is, does this approach outperform the state of the art, which is single source to single target transfer learning? And second, does this approach also lead to negative transfer or maybe not? So how did we design the study? We generated data with Builder. Therefore, we generated 450 source buildings. The number comes from the possible combinations of the variations. So you kind of plug this into the configuration file, the upper right. And if you multiply all different combinations by each other, you receive 450. And yeah, and then we did the same for the targets. So we for sure we use different values, different cities. A similar range though, but we wanted to show this method for single family houses in Central Europe, so that we don't have cooling system, but only a heating system, and the weather is, yeah, it's not the same for sure, but it's like this Mediterranean, like cold temperature weather. And yeah, so this is the data we used, and then we generate the data for 1 to 2 years. We used 1 year time series of each building from the 450 to now we're all the way on the right to train one general model G, which is an LSTM. And then we used 2 years of each building to generate one single source model, which is also an LSTM. For each of those models, we did a hyperparameter tuning so that we receive the best possible model for our specific building. And then when we go lower down here to the green part, that we assume to have little data available of our target, so 30 days. And we used the 30 days to fine-tune each of the available models up there. So for all the sources, for all the single sources, and for the general source on the right-hand side. Okay, and
When you do 30 days, which part of the year did you choose?
That's actually a good question. We use several starting points of the year, such that because we observed different behaviors. Since when you use January data, for sure, this leads to different results when you use summer data, and for that we found a new evaluation metric, which is included in the paper. I don't know if it's in the talk, in the appendix. Oh yeah, it's actually here. So what we did, we used 4 seasons of the year, and for each season we trained one model, because we assumed to have, okay, in the first iteration we might have winter data available, took 30 days of winter data and tested on the rest of the year, and then we reported the average error. And yeah, okay, so this is one result. For sure, we have way more experiments and ablations in the paper, but this is, I think, shows the results quite nicely. So what we see here first, the blue curve are the single source to single target results plotted as a percentage distribution. And down there you see the error metric, which is, we choose the maser, but also the RMSE is included. The maser compares the mean average error to the naive predictor, and the naive predictor takes the last value of the last time step as the naive forecast for the horizon, which we choose different horizons. In that example, it's 4 hours. And it kind of gives you a measure. So when you are on an error larger than 1, then your naive predictor is actually better than your model. So we use this metric kind of to find a very straightforward way to see if it's negative transfer or not. And yeah, and the green curve is the general source model fine-tuned to the specific targets. And the first thing we observe here quite nicely that the average error is quite lower for the general source model on average. So the dotted line is the average. And we also see the variance is a lot smaller. So we were very happy with the results. And also for a negative transfer, we didn't observe any errors larger than 1 for the general source model, but for the single sources, we saw quite a few. Okay, yeah, thereby we introduced the first multi-source approach for building thermodynamics. We could outperform the state of the art, which is the single source to single target transfer learning, and we didn't observe any negative transfer. And the paper is being published at the ACME Energy Conference in June, so it's in 1 month. Yeah, maybe I see some of you there.
3 of us will be there.
Ah, yeah, great. Yeah, so you can have maybe a more detailed talk on the paper if you want. Okay, and the code can be found on GitHub also. Yeah, so that's also an old project. Then a newer project, which I'm currently working on, and that's why I'm also here in Cambridge right now, because I'm doing this with a colleague from the energy group, for energy efficient cities from Ruchi, you know?
Oh, Richie.
Yeah. So the motivation behind this is basically what we've done before. So we have the general source model, and we used a little bit of data to fine-tune it, and then we basically tested it on the remaining year. But yeah, this is not how it's supposed to be, because when you move along in time, you would receive new data and you would want to do something with the data. So you should rather have something like this. So you would continuously fine-tune your model, you would always encompass the new data, and you would maybe also evaluate your model only on the next month or so in the consecutive order. Yeah, and thereby we can also investigate on certain changes in the building. So what happens if we have retrofits, or what happens if we have changes of occupants within the building. So this is kind of the motivation for this project. And this is kind of how the data stream looks like. So yeah, we would start even further on the left with the pre-trained model, and then we use the first interval of data, use this for fine-tuning, then the next consecutive time interval would be used for testing. We move along in time, and then at time instant t, you would have old data, which is x1 till xn minus 1, and you would have collected new data, which is xn, and you can do something with it. The question is what. And yeah, you would test on the next time period. And yeah, you would have several options out there. So the continual learning literature is increasing over the year. So especially the first 3 methods have been developed in the last 6 years, I think. So continual backpropagation, this is from last year. The other ones are a little bit older. These are just a few techniques to overcome the issues of catastrophic forgetting and plasticity, maybe, or loss of plasticity. Maybe you've heard of them. Catastrophic forgetting, maybe the name already says it quite nicely. So forgetting old knowledge, and plasticity means losing the ability, or plasticity means actually the ability to learn on new data. And the first study, continual backpropagation, they found after some time, some neurons become dormant, so that they actually don't do anything anymore. we didn't find this so far yet, like in the experiments I've done yet. I didn't see this yet, but yeah, it's we'll see how it evolves in the next couple of weeks. And also we can use, or we can apply those methods to fine-tune not only the past model of the time step n-1, we can also use the new data to fine-tune the general source model again, or we can also use all of the data to train a model from scratch. And yeah, so right now the experiments are not so straightforward. So I don't, so far I can't pick a good winner. So I'm kind of struggling with it right now, but it is also like a result that some or several methods might lead to the same results. And yeah, for sure, then we will investigate on certain changes in the environment. So that's a project that's going on. Then just
Can I ask a question about this?
Sure.
In this one, are you using the model for control as well?
No.
Okay, it's purely modeling.
Modeling of the thermal dynamics.
Good, because you're avoiding a big problem. If you're doing control based on an old model, then you'll be possibly not exploring the state space at all.
Yeah, I really want to do this later, or like after that. I kind of we don't have any expertise in control yet in our group, so I'm really excited to go into deeper in that.
Yeah, so one thing you could do with a real building, or is to actually look at non-occupant periods and do all your experiments when nobody's in the building. But then you can get the thermal parameters that way.
Yeah.
So at night when nobody's in the building, you can set the thermostat to 40 degrees.
Yeah.
Or whatever, and see what happens. You'll get all the conduction parameters for the walls and things like that. So if you do it by day, early in the morning, you get the radiative transfer inwards and so on. So, but just if you have occupancy, you can do a lot of tricks to extort the space, state space.
Yeah. Actually, I also have some ideas leading in that direction.
Okay.
But yeah, the topic of control is going to be touched soon.
Great.
Then another project that's going on, like I'm not working fully on that, but my colleague, and we're doing it together, it's just a very straightforward research question that is basically what is the best architecture to model building thermal dynamics? Because we saw when we did the other studies so far, or we had lots of discussions also with my professor, but also with reviewers. So yeah, what is actually the best architecture? Is it the LSTM, which has been used quite often in the literature, but it could be also transformers, for example, are currently state of the art for a lot of stuff. So maybe it's also for thermodynamics. And there's other options like state space models, for example, Mamba. New technologies you could use. So we're doing a paper on that also. And this is especially interesting regarding the data availability. So which architecture actually performs best when you have little data available versus you have maybe data of multiple buildings. So like a general model again, or having multiple years available.
Why aren't you doing graph neural networks? Because this is obviously a graph. You have rooms connected to other rooms.
Yeah.
You have some leakage parameters. So that suggests a graph neural network or more recently neural processes.
Yeah.
That's so the climate model people are moving towards neural processing. And so that might actually people in this room may know more about it than I do. The guys have put that GNNs and neural processes for process modeling.
I think the people in engineering,
Right, which is group, yeah.
is doing like Gaussian process and modeling and neural process.
Because from your perspective, you just have a time evolution of temperature in the room, driven the outside, and then how it affects the next room, right? So you have some ingress of external air and radiation, room processes, masses, and then wall. And so it's a process, a time evolution process.
Yeah, that's true.
It's very similar to what happens in planet model. So the aardvark model from Rich Miller's group, which just came out, was really breakthrough on planet modeling. So it might be worthwhile looking at that. Everything you have over here is actually at this point old fashioned. Right? LSTM is like, it's gone.
But it works quite good.
I know, but the thing work better.
Yeah, okay, yeah, maybe. It's a good idea to include it. Yeah, that's true. So I just started this project. And also another project, which is also, I think, kind of interesting, is this one, because you can, again, we're looking for the model F, but you can approximate each building with the RC circuit. So maybe you've heard of that. There are different approaches on how actually to model the RC circuit quite well, but this could be an example. And then the question is now how to find R and C. So this is unique again for your target building. And then there's a new approach which we want to investigate. It's actually from Thomas Gaskin. He's a maths PhD student from Cambridge. And yeah, it's a very nice idea on how to find the parameters. And that one works like that. So you have data again, very little data, 30 days. You use the data to input into a neural network, but the neural network actually outputs the parameters R and C of the network. And because you don't know them, but you know the structure of your RC circuit and you know the different differential equations, you can use those parameters, your estimates, plug them into your differential equation and simulate again, or solve this equation. And thereby you again receive data, which is the predicted data. And you calculate the loss then based on the predicted data versus the observed data. And use this as the loss.
Exactly what this is magic, you know.
Like the model inversion.
Yeah, it's exactly model inversion, because what you're doing neural networks invert the numerical solver to get the parameters from it.
Yeah.
So you should talk to Ihag. He's got a paper on this.
Oh, really? Okay.
Yeah.
Yeah, maybe you can send it to me.
Yeah.
Yeah, so
Unpublished.
archive.
Oh, yeah, that's good enough. Yeah.
We're still developing a model.
Nice. Very good. Yeah, it's just a small project that's also going on the side. And yeah, and this is just a brief summary. So we've talked today about Builder, the terminal building data generation framework for transfer learning, but also for other domains. We talked about Gentle, the general transfer learning model, and we have a lot of future work going on. Yeah, I talked about the first three, and the last one is also quite interesting. So basically, we're doing the same thing with the general pre-trained model, but now with reinforcement learning agents. So we try to train an agent not just on one building, but on multiple ones, and then deploy it in the target building. Yeah, and I'm very happy if you might be interested in one small of those topics, and I'm very happy if you want to reach out or discuss anything. Very happy for any kind of collaborations, and I would also be happy for, if nothing of this fits into you, I'm also happy just to catch a beer in the next week or something, since I'm still here, or a tea or coffee or something. Yeah, I'm just very happy to connect, and yeah, thank you for your attention.
Thank you.
This is the literature, and yeah, open to questions.
Andrew? Yeah.
As of course, talk a little bit more later, but can you speak more about the sources that you're using? Like, are they differentiated? I know you mentioned single family, but do you include maybe like flats and other?
No, it's so we applied this method only to single family houses in Central Europe, and yeah, so this is. We kind of designed the general model for this archetype of buildings. And because the underlying idea is maybe to have general models for specific archetypes, but maybe it's also, if you want to go large scale, you could also try to make a foundation model type of thing. But just for demonstration now, we stayed in this kind of domain here.
How did you settle on 450 sources? On the 450.
This is a project of all the different types.
Yes.
Yeah. So you just put it in the configuration file of Builder. Just type it in just like that, press play, wait 3 hours, and then you get like 450 CSV files.
If you increase the number of sources, what does that impact kind of?
The performance of it didn't change that much actually. So this was kind of a trade-off between computational resources and performance. It for sure it improved a little bit, but just slightly actually.
Yeah, also have a question about this slide. Wondering like for the multiple source versus target source, without fine-tuning, how large is the gap?
Of the
Like you train your model on multiple source data
yeah.
and you directly deploy your model on the target source. Do you have
The zero, you mean zero shot?
Yes.
Okay. That's like, it's actually not that bad actually. So zero shot, you receive, you would probably shift the green figure around like 0.1 to the right, approximately.
And when you build the multiple source, do you like include the parameter range of the target source or exclude that one?
Like for pre-training?
Yes.
No, it is not included. Only sources, no targets.
Yeah, but the target source you are going to apply your model to, that parameter range, you also include that in your multiple sources?
So this is the parameter range. Do you mean that?
Yeah.
Yeah, so you see here the U values, for example, they are in the same range as the U values of the sources. So it's kind of like the U values you see for the sources, they kind of demonstrate single family houses that are built between today and 1950. And they kind of demonstrate this range. Then you have so 1.3 is, for example, an older building. Then you have larger windows and smaller windows. You have different heating capacities depending on what material you used for building the building, and different sizes.
I can, so why did you all choose the Model based model?
That's a good question. I think we because Energy Plus would be the other option, which I think is also quite does a good modeling job, but we wanted to set all of the parameters with Python, and we came to the conclusion it was a little bit easier with the Modelica model. But also in the future, we want to include the HVAC or like the heating system, and also like a battery storage unit and stuff like that. More in particular, so you can maybe also put in a heat pump, because this is currently not possible. You only have cooling, heating and ventilation, but no heat pump, no gas thermal unit, stuff like that. And that can be modeled better with Modelica.
Have you all explored what this would look like? I believe the gentle framework focuses on using just this generated data here. Have you looked at the real source data?
Yeah, we tried, but we couldn't really find good data. So what we did, we tested it on there's a synthetic data set out there. I think it's called a synthetic data operation data set or something. I'm not sure if you've heard of it. And we did basically the same study with that, and we received very similar results. Yeah, but we couldn't find any real data yet. I was going to talk to Zoltan Nagy. I think you maybe know him.
Yes.
Yeah. So we already talked on via email, and he sent me a few data sets, but yeah. But so far no real data basically fits this approach. But we are also doing a project with the industry right now, where we at least want to test. Or actually what we do is we come from the simulation side and we test it in the real building out there. So there's like a sim to real transfer. but with this approach.
Does Germany have these building architects? Standard architects, like code architects here? Or...
I think so, yeah. Like
Okay.
multi-family house, single-family house.
Yeah, yes, things like that.
Yeah.
Okay. But I mean, then that would be other way for you to get for your build. That would be to use those as the input files as the base, and then you could vary those to see get your sources for projects.
That's actually what we did here. So this is called the tabular dataset.
Yes.
Do you know it?
Oh, well, I know what other tabulators is. I remember the German one.
Yeah, but no, we use the tabular
Okay.
dataset. Yeah.
Okay. Sorry, tabula.
Yeah.
I haven't heard of that one. No.
Typologically, I don't know.
Okay.
It gives you the parameter ranges of the buildings out there. Yeah.
Okay, I think maybe Andre, you probably have a lot more to talk about, but we should maybe a little bit outside the range of interest of some of the people here. So why don't we stop here? Thank you very much.
Yeah, thank you.
We'll continue with a few people perhaps, and I will stop the recording here.